project, we focused on permeability because just like Dr. White said, the single most important rock property for flow is the permeability. So mainly in our project, we're going to focus on the various relationships that permeability shares with a variety of factors. And my name is Andrew Thornton.
I'm Robert Schnadelbeck.
Patrick Ryan.
And Andrew Broom.
Permeability is an intrinsic property of reservoir rock that estimates the flow capacity of that reservoir. In other words, it's the measure of the ability of a porous medium to transmit fluids. There are three types of permeability. First, relative permeability, which is the ratio of effective permeability of a fluid at a certain saturation to a base permeability. Secondly, we have effective permeability, which is the permeability of a rock to a fluid in a two-phase system. And last, we have absolute permeability, also intrinsic permeability, which is measured using a single fluid in a rock. Mostly done using air, but we'll be using water in our experiment. The differences in permeability and porosity. Permeability depends on the shape, sorting, pore, grain size, and the packing of the particles. The material must be porous to be permeable, but not the other way around. Porosity, on the other hand, it doesn't depend on grain size, but it is affected by grain packing, which generally ranges between 1 to 35% in carbonate reservoirs. Carbon-Cozzini managed to devise a formula to relate the two, as seen here. Some of the factors affecting permeability are the textural properties, gas slippage, the amount of distribution and type of clays, the overburden pressure, high velocity flow rates, and water saturation. All these topics will be discussed shortly. Some of the textural properties that affect permeability are the pore grain size, grain sorting, shape of grains, and grain packing. Gas slippage. Gas slippage basically is saying gas molecules encounter less resistance, thus moving more freely, which results in an artificial increase in permeability. Klinkenberg managed to devise a formula to account for this artificial increase.
The amount of distribution and types of clays. How does a clay affect the permeability? It's a lot. Clay is obviously thicker than less permeable than sandstone and other things you might encounter, but increased clay content in sandstones directly correlates to a decrease in both permeability and porosity of the formation. And like I said, it's just due to the fact that it's less permeable. In diagenesis, process by which sediments are lithified into sedimentary rock. And there's athogenic interstitial clays, which are clays that form these crystals within the pore space, making it less porous. And there's allogenic clays, which come from elsewhere, other parts of the formation. And then there's the effects of the overburden pressure. There's cementation of grains. Again, there's confining pressures that affects the porosity, which affects permeability. And like I said, the cementation of these grains are going to compact everything together and make everything less porous. And there's two different types of applied stress, triaxial and hydrostatic. And I'll go into more of these in greater depth later, but basically triaxial is when the two sides, like the axial stresses are higher than the hydrostatic forces, and hydrostatic is, like I said, the hydrostatic forces from the top. And pressures increase as rocks are buried deeper, which just goes to show like the layers on top are gonna add to the pressure of the layers on the bottom. And an increase in overburden pressure corresponds to a decrease in both porosity and permeability, which just this cramping done by the overburden pressure is going to make everything tighter, less porosity, less permeability. And then this is the equation to calculate overburden pressure. It's kind of complicated, but G is the acceleration due to gravity, P0 is the pressure of the datum, and PZ is the density of the overlying rock. It kind of breaks it down to three easy equations, or three easy variables. And the assumption that gravity does not change with height, that's what you have to make when doing this, but in reality it does change slightly when you get closer to the Earth's center, but we usually don't count that. And there is a hydrostatic stress effects on permeability, and permeability of rock decreases with the increase in applied stress. And this causes the fluid to take the path of least resistance, which is usually the fractures, which form during the stress. And this is because the effective permeability is higher on these fractures than the matrix, and so this fluid will be able to go in these areas with greater permeability than there are in the matrix of the formation. And this actually has the highest effect on permeability, higher than the triaxial, which we'll get to soon. We simulated in our experiment. We did simulate this by compacting sand. In our experiment, we had non-compacted and compacted sand, and we found that in our experiment, obviously you've probably already seen, but the compacted sand took way longer for the flow rate to go, or for the liquid to go through it, a lower flow rate. And now it's in the triaxial stress. Triaxial stress state is a condition in which axial stresses are lesser than the overburden pressure. This is because permeability of rock decreases with the increase of implied stress, and this increases the fluid flow, and the effective permeability decreases with an increase in triaxial stress. The flow rate also decreases with increase in triaxial stress, just because the same reason that just it's an overburden pressure, so this will cramp everything. This is a cramping kind of stress that affects.
All right, pressures induced permeability change by formation type. Basically, here are three major formation types that are found in the Earth strata. The sandstones, you have clay, and you have granite. All right, basically we have permeability anisotropy, which it varies by direction, and it's better with parallel flow and fractures and stuff, and moves a lot easier in parallel flow. And then you also have the grain shape, which is oblate and prolate. Oblate would be a more flattened grain, and then the prolate would be an elongated grain. You also have tortuosity, which is inversely proportional to the permeability. Tortuosity is basically the winding path in the porous media that will affect the flow rate going through it. So here's anisotropy again, and like I said, it varies on permeability with direction. Better parallel flow, and a good example would be fluid traveling up a tree. You can't have fluid going against the grain, perpendicular to the grain. It's better to go parallel with the grain. And it's different from heterogeneity. Heterogeneity is basically a compaction of the Earth's strata. You're going to have different permeability in every part of the strata you're looking at, and it's a good parallel or series flow.
The productivity of a well is strongly influenced by the permeability of the formation that you're producing from. Conventional reservoirs, on average, have good permeability and an attractive production rate. Unconventional reservoirs, such as shale fracking, have typically low permeability values, slightly less than 0.01 millidarcies, and generally unproductive production rates. For flow in layered domains, there's two different types of flow. You have parallel flow, which is kind of going through along the grains between strata, and series flow, which is more coming up the grains through the strata. As you see, each layer of strata has its own height and permeability that's specific to the strata itself. There are simple ways to calculate this for linear situations. For series flow, you just, a little calculation right there. Parallel flow, we've got a very similar one too. Simple algebra can easily be calculated for estimation.
For our experiment, we have a bunch of equipment here, but I'll start with the three identical tubes. They're all clear so you can see what's going on inside of it. And they're going to be draining the water through to the three measuring cups, which you have underneath. And we're going to be pouring water from they're 1 liter bottles, but we only fill them halfway, so they're half liters. And these are connected to the screens to keep the gravel and the sand and the compacted sand in from leaking while we have the water going through them.
Okay, today for our experiment, the first thing we did was bound the mesh to each of the tubes to hold our rocks up. Second, we filled our gravel tube to a height of 18 inches. After that, we filled our middle tube, which is just unconsolidated sand, also to a height of 18 inches. Third, we filled our third tube up to a height of 24 inches, then used a prod to pack it down to simulate compacted sand or overburden pressure, down to a height of 18 inches as well.
Alright, for our experiment today involves the simulation of flow through our homemade core samples. We're going to measure the time it takes for 250 milliliters of water to pass through each core so that we could use the Darcy's equation to estimate the permeabilities of each core. And now we're about to begin our experiment.
What we expect to find is that the grains will be the highest permeability, followed by the sand, and then lastly by the compact sand, or the overburden pressure sand.
I'll be using my iPhone to check the time that it takes for 250 milliliters to pass through each of our cores. Ready? Go. Took about 28 seconds for this core to drain, proving our initial estimation correct. You can see the slight difference in hydrostatic head, which would suggest that the flow rate is slightly faster in our unconsolidated sand, without accounting for the difference in pressure caused by that hydrostatic head.
Okay. It's been 3 minutes and 30 seconds since we stopped the video, and we hit the 50 milliliter mark for the regular sand, and we're still waiting for the packed sand to reach that mark. This is going way faster than the packed sand, as you can see. We're still waiting for it, to drain. It's going to take a while, so we'll see y'all in a little bit.
Hey, also, it's been about 5 minutes since we last saw each other. Our third core has just reached 150 milliliters drained. It is by far the slowest flow rate of all three of our cores, which proves our initial estimations once again correct. We'll tune back in once we're finished draining everything.
It has now been 22 minutes and 50 seconds, and we have just hit 250 milliliters on our compacted sand.
Through our experiment, we were able to calculate average flow rates for each core. Then we used the average flow rates in the Darcy potential flow rate equation to calculate each permeability. Our results are displayed behind me on a logarithmic scale, with the y-axis representing millidarcies. As you can see here, our initial estimate that the gravel core would have the highest permeability, it seems to be pretty accurate, followed by the unconsolidated sand, and lastly the compact sand.